Hi, everyone. Okay, afternoon. So this is the first physics colloquium. We haven't had physics colloquia in a long time. I think it's a very good idea for us to start this tradition of having colloquia. We all know in the theory group, we've had regular seminars for now decades. But I think it's a very good idea for us to have a departmental colloquium, and where all students, PGR students, and all experimentalists and theorists can all join in. And when the term is on, we'll have our undergraduate students also joining in, probably in a different place, so we have enough capacity. So it's great to have a distinguished visitor, Professor Gerard Milburn, to give the first of our physics colloquia. And I think Sahar will actually give you an introduction to the speaker.
Thank you, Fred. Thanks everyone for coming. Welcome to this colloquium talk. And today we are very fortunate to have Professor Gerard Milburn from the University of Queensland Center for Engineered Quantum Systems. Gerard is very famous for his works on quantum optics, atom optics, quantum stochastic processes, quantum engineered systems, and quantum control, and the list goes on and on. He has written some famous, very interesting textbooks on quantum optics, quantum engineering and control, and a recent one on optomechanics, which are all highly recommendable. But he also has a couple of other popular books. One of them is called Schrödinger Machines, which was published in 1997. And it gives a very interesting introduction on how in 50 years' time, quantum technologies can change the view of the world. Perhaps at the time, it seemed more like a science fiction, but then in 2011, Gerard became the founder of Australian Research Council Centre of Excellence for Engineered Quantum Systems, which was one of the pioneering centers which stepped in this revolution to quantum technologies. And perhaps some of you know Gerard for his pioneering paper published in 2001, together with Neil and Laflamme, in which he introduced the scheme of doing quantum computation using linear optics. And this work had a major impact on the field of optical quantum computing. Gerard has recently been working on quantum learning machines, and he has publications on some non-conventional aspects of machine learning and the links to thermodynamics. But today he will be talking about a slightly different topic, which will probably be very interesting for the participants here. And it is lab-based test of gravitational decoherence. Gerard, thank you very much for being with us, and you're welcome to start your presentation.
Thank you, Sahar. Thanks, Sahar. That was a great introduction. The early non-technical books I wrote were regrettably not popular. Otherwise, perhaps I would have pursued a different career. Perhaps it's a good thing. As you say, they were written a very long time ago. The one, Schrödinger's Machines, was published in Australia as Quantum Technology. But when the young publisher offered it to the American publisher, he said, "Oh, that's a terrible title. No one's going to want to read a book called that." So they decided to change it to Schrödinger's Machines, because at the time there were books like Schrödinger's Cat and Schrödinger's Breakfast, and so Schrödinger's Machines seemed to fit. So thanks very much for the introduction. So the subject of well, actually, I should also say it's great to be here in Swansea. I haven't really been to South Wales much. I went to Rossley Beach once a few years ago, and it's great. You know, I could tell my friends back in Australia, I'm in Old South Wales, which is a nice change from New South Wales. But the sun shines and the beaches are great, and it's really very enjoyable. And also great physics, talking to Sahar and Ardalan about various research projects. But the subject today is not about any of those things. It's about work I started about 20 years ago on trying to understand if there was any possible way to find experimental evidence for quantum effects in gravity. And in many ways, it was an attempt to test quantum mechanics to destruction. We all know that quantum mechanics is amazingly successful, deeply puzzling, but amazingly successful. And we can now engineer quantum systems de novo according to a set of functions that we specify in advance. It works incredibly well. So where could we ever hope to find some place it would fail? And it seemed to me at the time, and to many others, that the obvious place was the interface between gravitational physics, or general relativity, and quantum mechanics. Now, at the time, the consensus was that there was little point in thinking about experimental tests of quantum gravity because the energy scales involved would be enormous. To probe things at the Planck length, which is a very small distance, requires enormous energy, largely because of the uncertainty principle. If you think about it, if you need to localize something at 10 to the minus 33 meters, then the uncertainty in momentum is going to be enormous, and the energy varies as the uncertainty in momentum. But another thread tried to look at what would happen if gravity was quantum and exerted a more subtle effect on everyday quantum mechanics called decoherence, and that's the subject of this talk. Okay, so let's begin. Well, better point it this way, I suppose. No, it's not that one. It's not. Oops. I'll just use this. So, yeah, it's fine. The difficulty's been around a very long time. I could have gone to many people to introduce it, but perhaps the clearest introduction to why we need a quantum theory of gravity came in this very famous conference in Chapel Hill in 1957, where Feynman, in response to a criticism or a question from somebody in the audience, had all the famous relativists there like Wheeler and Bryce DeWitt. He said, we're in trouble if we believe in quantum mechanics, but don't quantize gravitational theory. And I'll explain throughout the talk why that's a problem. So it's been known for a long time that this was a pressing need. So what is the problem? So the basic issue is this. Imagine you have one particle, not two, one single massive particle, and you place it in a superposition of two positions, to the left of the origin or the right of the origin. Now it's one particle, and of course, in 1957, this would have been very difficult to do. Now, with advances in optomechanics and ion trapping, it's not so difficult to do. But now you ask yourself, if we have a single particle placed in a superposition, what is the gravitational field of that massive object? You might think, oh, well, the gravitational field is just the average mass density. But that won't work, because if you do what you're supposed to do when you're mapping out a gravitational field and let test particles propagate in this system, then they will sometimes be deflected to the left and sometimes be deflected to the right. Because the particle is a superposition, the deflection is essentially a measurement of which side of the origin the particle is on. However, if it was an equal density of the masses, it wouldn't be deflected at all, because the gravitational field at the center would be zero. So clearly it cannot be a superposition of two mass densities. In any case, if it was a superposition of two mass densities, the mutual gravitation between them would cause them to come together. But we only have one particle in the system. So at some point you'll hear a little click as the particles hit, and that would be a clear manifestation of the sound of one hand clapping. So that doesn't make much sense. But this key idea that it leads to fluctuations in forces exerted on test particles indicates straight off that what it really means is fluctuations in the structure of space-time itself, if you're able to do this. Of course, we know that if it's a measurement, it will decohere the superposition. So if you try to do the measurement, you will find it either on the left or the right. It'll just fluctuate 50% one way or 50% the other. We talk about that as decoherence. It's destroyed the coherent superposition, and the particle is localized from one trial to the next. Now, you don't have to do it with spatial deflections. You can also look at redshifts. Imagine we had a mass, again, a single massive object in a superposition of two positions, and you bring a clock up towards it. Then the one further from the clock will have less of a gravitational redshift than the one closest to the clock. Again, it will be a measurement of where the particle is. Large redshift close to the clock, small redshift further from the clock. So we see that a superposition of gravitational fields will necessarily lead to fluctuations in local time as well. So to summarize it, we basically have a way of causing fluctuations in the space-time metric itself, using rulers to measure fluctuations in spatial geometry, or clocks to measure fluctuations in local time. And it will also lead to fluctuations in the causal structure, which is determined by how light rays bend. There'll be a different bending for one superposition and the other. Now, obviously, for a lab-based mass, it's going to be incredibly small, but that's really not the point. It's the principle that's the issue. So such a superposition cannot be a stationary state of Einstein's equations. It simply cannot be a stationary state because it leads to fluctuations in the metric and the causal structure of space-time itself. And furthermore, you might ask, well, surely this is no different from electromagnetism. Well, there's a very big well, there are two big differences. Firstly, electromagnetism has two charges and gravity only has one. It simply has a mass. So that makes a huge difference when you look at the thermodynamics. And secondly, you can't shield against gravity because gravitation is space-time curvature. Often when I've given this talk, somebody rushes up to me at the end and said they've figured out a way to shield against gravity. But I promise you there is none, except perhaps using some exotic form of matter with negative energy density or something along those lines. But for conventional general relativity, there's no way to shield against gravity. That means there's always an open channel. Somewhere, someone could detect the gravitational field even within a completely closed box from the point of view of every other quantum observation you might like to make upon it. So that makes gravity very different. Here's another way to think about gravitational decoherence, which I'll come back to a number of times, and that is it's deeply connected to the ability to make a superposition. So let's imagine we have a particle, a massive particle located on the left with certainty, the standard situation. Then we somehow or other manage to put it into a superposition of two different places, perhaps doing some sort of atom optical Stern-Gerlach experiment, where ground state particles get deflected to the right and excited state particles get deflected to the left, and we put it in a superposition of ground and excited state so it coherently splits. We wait a while and then just invert that and bring it back. So if everything is unitary, we should be able to bring it all the way back. It's just like an interferometer. But if there's some measurement channel or some decoherence going on, and I just suggested there's always a measurement channel, then there'll be a finite probability to find it on the right rather than the left when you bring it back. So here, a little learning is always a dangerous thing from the point of view of producing a coherent superposition of two masses. Any measurement channel, no matter how weak, can in principle decohere. Of course, it's all going to come down to a matter of degrees and numbers, and that's what lab-based tests are all about, finding what the bounds on those numbers will be. Okay, now perhaps the person who had the most input into this idea that gravitation and quantum physics will lead to some sort of intrinsic decoherence was Roger Penrose, who in 1996, actually he wasn't the first, there's another one I'll come to in a minute, but his one got a lot of traction, looked at exactly these situations where you have the center of mass superposition of an object at -d and its associated gravitational field. I'm writing it as a quantum state, but of course we haven't got a quantum theory of gravity, so I have no idea what that symbol refers to, but assuming somehow rather it should be quantum. And likewise here, there's a different gravitational field. And as I've just argued, this cannot be a stationary state. It cannot be an energy eigenstate of matter plus gravity, simply because we'll always see fluctuations in the space-time metric in such a situation. And on the basis of that, Penrose argued there must be an intrinsic instability in quantum coherence when gravitational fields are significant, by which he meant that as you try to make the superposition bigger and bigger and bigger, it'll spontaneously collapse into one side or the other. Now, we know of nothing in quantum mechanics that behaves like that, so that's clearly outside standard quantum physics. There's a whole literature on spontaneous collapse going back to Girardi, Rimini, and Weber, but there's no evidence for it whatsoever. It was largely introduced to try and step around conceptual problems, but there's no evidence for it. He even estimated the rate of decay using the uncertainty principle, the energy time uncertainty principle, And by looking at how particles are deflected in the potentials, that's where these gradients of the potentials comes from, he was able to write down an expression for delta, which has units of energy. And it's basically the mass energy, the difference. So this is the difference in density, spatial density, of a particle located over there and a particle located over there. So something like the self-energy of the superposition. It's pretty hard to picture. And it's also extremely hard to calculate because, you know, if you have a lump of matter, do you use a continuum approximation to compute the mass density? Given that you're going to be separating these things only by a little bit, maybe that's not a good idea. Do you use the nuclear density to calculate it? So there's a great deal of ambiguity in this expression, but it's not a bad idea. It seems physically well motivated, and it led to a considerable program. Well, not a considerable program. A few brave souls decided to set out to do some experiments. I'll describe them in a minute. Let me give you an analogy of why that kind of argument suggests spontaneous collapse, and it comes from an equivalent argument in quantum electrodynamics called spontaneous emission, which I hope you're all familiar with. Imagine we have an atom in the ground state and the vacuum state of the field. So low temperature optical fields or something. The atom's in the ground state, the field is in the ground state. That's clearly an energy eigenstate of quantum electrodynamics. It has no dynamics at all, it just sits there. We know there are fluctuations, of course, but that depends on the kind of measurements you're going to do. It still just sits there, stationary state of quantum electrodynamics. However, if we have a local quench, we go and find one of these atoms and give it a little kick with a pulse of light, it's called a quench, then it will now go into a combination of, it'll go into the excited state if you do it right, which means that it's no longer a stationary state of the electromagnetic field, because that is not an energy state of the electromagnetic field, it's some slightly excited state. So therefore, it instantly has to start evolving into all the energy eigenstates of the electromagnetic field, which will involve the initial, the field in the vacuum state and the atom in the excited state. Oops, I got this around the wrong way. They should be around the other way. But the essential idea is this, that it has to evolve into a state where the atom is in the ground state and the field is in some excited state, because I've kicked it up to the excited state. It now begins to entangle with all the many modes of the radiation field. And we know that if we trace out the radiation field, because it's a very, very large many-bodied system, we see spontaneous emission. So the probability to find the atom in the ground state after the quench is an exponentially decaying function of time. It's a direct consequence of quantum entanglement between a locally excited system and the many-body system that surrounds it, in this case, the electromagnetic field. So that's, I think, was part of Penrose's intuition. Now, there's another direction of arguing for quantum decoherence, and it comes from trying to quantize gravity directly in Einstein's equations. This has a very long tradition of, a lot of confusion and some success. But the problem is, on this side we have space-time, and on this side we have matter in terms of the stress-energy tensor. Now we know that, in fact, this side is quantum fields of one sort or another. So what do we put there if we have quantum sources when this side is entirely classical? The standard thing to try is something like mean field theory, which is to just replace this operator, which if it's involving all the matter fields involved will now become some operator. Just replace it by its average value in some state. That's like mean field theory. And that's fine if there is a mean field, but the sorts of superpositions I was looking at before are in fact precisely the ones that have a zero mean field at the origin. So it won't work for those. It may work for some semi-classical states, but in general, it will fail. And it's also a pretty uncontrolled approximation in the case of quantum electrodynamics. Now, there was a whole literature in going the other way and saying, let's put in space-time curvature of one sort or another and ask how do quantum fields propagate on that space-time background without actually acting on the space-time background. And the classic text in this field was by Birrell and Davies, called Quantum Fields in Curved Space-Time. It's an extremely elegant mathematical subject. Hawking radiation is one of the key results of that field. But it's plagued with conceptual difficulties. In particular, the fact that there is no unique vacuum in curved space-time. We're all used to the vacuum state of the field in flat space-time. It's universal, it's everywhere. But in curved space-time, there is no unique vacuum, so there's no unique notion of particle. What's vacuum for one region of space-time is not vacuum for some other region of space-time. And to see that, you need to consider the modes of a source and detector and how they couple to the electromagnetic field. And because it's in a non-flat background, they change dramatically. Just gravitational redshift is a good example. In any case, Diosi decided to try and make sense of consistently combining classical physics, classical dynamics with quantum dynamics. So this other approach to gravitational decoherence is due to this attempt to combine classical and quantum dynamics into the same equation. Now we know this is going to be problematic because while we can easily put classical forces into the Heisenberg equations of motion, we do that all the time, putting quantum objects into the Hamilton's equations of motion makes no sense at all, because we just have ordinary position and momentum functions with operators turning up in there, just like in this problem. So what Diosi reasoned in this very elegant paper, I should have put where it was published, I didn't check that. He argued that there is a consistent way to do it, and there are ways to justify this based on measurement, which I won't go into, but the basic idea is this. If you try to put quantum sources into Hamilton's equations of motion, you'll quickly get a violation of the uncertainty principle. So Diosi's idea was to add just enough noise to the classical equations and just enough noise to the quantum equations to prevent any violation of the uncertainty principle. So in this equation, which is apparently called the Alexandrov bracket, you have the usual quantum dynamics and with a density operator, but you have the classical phase space coordinates of some particle as well. And then there's a way of adding noise to both so that this becomes just diffusion in momentum and this becomes decoherence in position. And so long as the product of that times that rate is greater than h bar squared on 4, you'll never run into any problems of non-positivity of the density matrix, no problems with the Heisenberg uncertainty principle. Now, it's perfectly innocuous to add noise to classical equations. We all do that when we're describing Brownian motion. It just adds momentum diffusion. But when you put noise into a quantum equation, sure, it adds momentum diffusion, but the quantum consequence of that is it implies decoherence in the conjugate basis, the position basis. So the minute you try to reconcile classical and quantum dynamics in this way, you're basically introducing an intrinsic decoherence mechanism into the quantum dynamics. In particular, it takes this rather special form with a double commutator with position. I'll come back to this in a minute. But driving momentum fluctuations in some intrinsic way violates conservation of energy, because that will look like heating from the point of view of an experimentalist. So what seemed like a good idea at the time has these rather unfortunate consequences of violating energy conservation in general. And in fact, that's a feature of almost all, but not all, as I'll describe, models of spontaneous collapse and intrinsic decoherence. They nearly all violate, except one special class, violate energy conservation.
Can I ask a question?
Sure.
So this equation that's written down, it's probably not derived from
No.
first principles.
No,
but there is a first principles way to actually go about this problem.
Yes.
You start with quantum fields coupled to gravity and on a classical background, and then include the fluctuations of the metric around that classical background.
Yep.
And then integrate out the fluctuations order by order,
systematically,
and try to derive such an equation, get an influence function.
Yep.
There's systematically. Has anybody done this? And
I think so.
basis?
Yes, I
Is
think
this the right equation?
It's something like this. Yes, that's correct. But that will explain the physical origins of these fluctuations. They won't be intrinsic. You'll be able to point to where they come from. There'll be fluctuations in the metric or something like that. So there is a self-consistent way to do that. But both Penrose and Diosi were claiming it was some, in principle, modification of quantum mechanics. We'd be familiar with this sort of thing in say, ordinary many-body quantum physics, where we might want to factor out some large collective degree of freedom. Then the microscopic degrees of freedom would just remain as a source of noise and uncertainty and decoherence. That's also what happens in many-body physics. Amazingly, Diosi was able to calculate a rate for the decoherence which apart from a few factors is indistinguishable from the Penrose result, but coming at it from a completely different direction. But they both share the feature that decoherence takes place in the position basis, which means heating. So initially, people thought, well, let's go after the heating, which is easier than it's much more difficult than it sounds, because virtually everything heats. The only way to stop something from heating is to put it in a Faraday cage and reduce the temperature and all the rest of it until everything else is gone except gravity, which you can't shield, and then see there's some underlying heating going on. So that experiment was tried a year or so, was it last year or the year before, in Gran Sasso in Italy, and it failed to find any evidence of heating. But there are other reasons why one would doubt the Penrose-Diosi approach. And one I've already mentioned is the technical difficulties of computing the decoherence rate in terms of mass energy densities. That's really hard and very ambiguous as to what you should put in. But there's a best guess, and it was the best guess that wasn't seen in the Gran Sasso experiment. The other problem with this is it's completely silent on what happens in the optical sector for massless particles. And gravity should tell you there's something going on about decoherence for photons as well, but this is completely silent because it's totally focused on deflections of particles from a gravitational potential. So there are a couple of problems. So decoherence in position basis implies heating and momentum. And this beautiful experiment done actually was last year, found no evidence of heating, even to the point where they said, our result sets a lower bound on the effective size of the mass density of nuclei, which is about 3 orders of magnitude larger than previous bounds. And this experiment rules out natural parameter-free versions of the Diosi-Penrose model, which certainly sounds like initial bad news. I'm sure they were disappointed. It would have been a big deal if they'd found it, but no such luck. Now, what else can we do besides looking for heating? Well, one idea was suggested by Stephanie Vanna, who at the time was in Australia, I think, but by the time I did this work with her, she was in Delft in the Center for Quantum Nanoscience in Delft. And the basic idea here is to use a concept from quantum information theory, and that is LOCC, local operations, by which I mean applying forces and making measurements locally, plus classical communication, that is sending classical signals, radio waves or something, cannot entangle two particles that are not local. Now, gravity is certainly some sort of classical channel if it's treated classically, right? Sort of a black hole collides with a black hole somewhere out there in the universe and we see mirrors wiggle in LIGO. It's certainly some sort of communication channel, but if it's classical, it means we'll never be able to entangle anything with gravity, which would be a major break from our understanding of the rest of quantum mechanics. And it goes back to Feynman's point that if you really take quantum mechanics seriously, you really should worry about quantizing gravity, quite apart from any technical aesthetics involved. So Stephanie and I and a couple of students came up with a method for looking for what's known as an entanglement witness. And the basic idea is this: if you have two entangled particles, and one gets entangled with something else via some unknown process, you may never know what it is. But if you try and measure the entanglement here, you will see that that has happened. And by looking at the details of how the entanglement is diminished, you might be able to learn something about what this unknown process is. That's the basic idea for an entanglement witness. And we came up with a scheme based on optomechanics, which I'll say a little bit about later, that showed it was possible. If you have a model, I mean, you can't really predict what numbers you should see unless you have a model for what's in the box. So we stuck in Penrose-Diosi type models, and we found that at very low temperatures, there would indeed be a smoking gun in the diminishment of entanglement in this problem. So this is another way to go after Penrose-Diosi, not related to heating, but related to actual decoherence or loss of entanglement. Since then, there's been a number of proposals for an entanglement witness. One was some work I did with Sugata Bose and a bunch of other people. We started in 2015, I think, and it wasn't published till 2017, based on a spin entanglement witness, which I'll talk about. And completely independently, Chiara Mileto and Vlatko Vedrol came up with a very similar scheme published in back-to-back, as you can see in the same issue of Physical Review Letters. So here's the idea behind the spin entanglement scheme that I was involved in. Here are all the other authors. So the basic idea is, again, not to have a single particle in a superposition of two positions, but have two particles in a superposition of two positions. And now there are 4 possible gravitational interactions between that one and that one, that one and that one, that one and that one, and that one and that one. So if you can somehow or other produce this superposition of two particles, they should acquire some relative phases depending on which particular branch of the wave function you're in. So the idea was to come up with some sort of Stern-Gerlach experiment, which, depending on an internal degree of freedom like spin, deflected one particle to the left or the right, and the other particle to the left or the right. So you did indeed have these kind of 4 types of gravitational interactions, and then just let them fall, and then disentangle by inverting this Stern-Gerlach device down here, and asking that transfers the entanglement to the internal degree of freedom, and then measure the spin as accurately as you possibly can, which in an optical experiment could be done using diamond NV centers, or it could be done using some other internal spin degree of freedom. So that was the idea. This symbol here is meant to represent Newtonian fluctuations in the gravitational field at very low energies. So the idea is you make a superposition of left and right. If that was the case without internal degrees of freedom, you'd find there'd be a different phase involving L1, R2 compared to R1, L2. They would have a different phase because some are close together, some are far apart, and the other two is a kind of common channel. And you can work out what those phases are, not very difficult to work out. They depend on the product of the masses and G, and basically turns out to be the derivative of the gravitational potential. Now, the trick is to write that phase into the internal degree of freedom. And this is what an entanglement witness does. So putting in the spin degrees of freedom, the first thing you do is create a spin superposition. Then you pass it through this sort of optical Stern-Gerlach device. So one center of mass goes one way and one center of mass goes the other way. In the optical case, it would be an atom in the ground state in a dispersive electromagnetic field, say a standing wave. The ground state will get a positive momentum kick, and the excited state will get a negative momentum kick. It's just induced dipole forces. Then you let it fall so that it acquires these phases, and then you undo the spin superposition. And the net effect is that you end up writing the gravitational phases into the internal degree of freedom, and the external degrees of freedom of the gravitational field should factor out. So now you can just go in and look at the spin entanglement. And to do that, you have to measure lots and lots of spin correlations of this form, X on one and Z on the other, and Y on one and Y on the other. Actually, I should have think that should have been X. X, X, Y, Y is what it is. And if W is greater than 1, it's entangled. Otherwise, it's not. So needless to say, it's a very small effect, but we believe it's possible. And taking a diamond nanocrystal, an NV center, this is a little piece of diamond with an electron vacancy center, which has a spin polarization, mass of 10 to the minus 14, possible splitting of about 250 microns, which is perfectly conceivable in these sorts of experiments, and a fall time of 2.5 seconds, again, not outrageous in terms of laboratory practice. Then you find these two phases are quite different, and then you would predict a W of 1.17 if they were truly entangled. So this would tell you, if you get W greater than 1, that gravity has to be quantized. Of course, we all expect that anyway. If it comes out less than 1, then we're going to be deeply surprised and deeply troubled, because that would be a major break with any physics that we understand. At least knowing that gravity is quantized as a start, what we then need to do is to come up with models of quantum gravity to predict what W should be, or at least use W to put bounds on possible extensions of gravity into some quantum domain. So when I say lab-based tests of gravitational decoherence and quantum gravity, it's these kinds of things that I'm referring to. When we first started discussing this years ago, the string theorists and high energy particle physicists didn't want a bar of it because they thought it would be, there was no way you're going to do tests of quantum gravity in the laboratory because it's going to, as I said, require such huge energies. But this shows that there is a way to access it in the lab. Sure, it's difficult. It pushes the absolute limits of quantum technology developed for other reasons, but it's not inconceivable. Now, of course, there's other forms of decoherence going on in this. One is collisions with gas molecules as these little NV diamond crystals fall. Another is spin dephasing due to nuclei or impurities in the diamond. The other is Casimir-Polder. If you've got two little diamond nanocrystals close together, then Casimir-Polder forces need to be taken into account. But if you choose the separation big enough, you can show that that will be negligible. Nonetheless, they all put bounds on the required experiment you need to do. So it has to be a good vacuum, very cold, and the splitting has to be extremely coherent at the very beginnings. So it's difficult, not impossible, and is underway. Now, long before those ideas came along, Dick Baumeister, working with Roger Penrose and Christoph Siemann and others, came up with an optomechanical way of looking for gravitational decoherence. In optomechanics, basically what happens is you're using the radiation pressure force to excite some mechanical motion. So if there's a mirror on the end of a spring and it reflects a photon, then it gets a little recoil, gets a little impulse on it. And so it starts to oscillate. And so if you put a photon into a superposition of one going up and one going this way, then which mirror gets the kick will also be a superposition. And so again, you'll have some sort of coherent superposition of different motions, different mechanical motions of the mirror. And that, it was hoped, would enable some sort of test of gravitational decoherence. Since then, there have been many, many proposals. Here's one that I looked at some years ago. We do something like a back-to-back LIGO. So we have two suspended mirrors acting as simple harmonic oscillators as the end mirrors of two cavities. Then we take an entangled photon source and we reflect it into this cavity and it comes back out, because it has to come back out if that's perfectly reflecting, assuming you do all the optics right and it doesn't get scattered. Likewise, this one has to come back out. So if it's not getting entangled in here, these should be identical if the whole thing is completely symmetric. In other words, the entanglement of the photons won't be diminished by its interaction with those moving mirrors. But if the gravitational interaction between these things is taken into account and it's mediated by a quantum degree of freedom, then the entanglement of the photons coming out would be reduced. And you could easily check that by a standard Bell-type experiment on two photons, which have been done for 30 years to ever increasing degrees of precision. So that's one way to do it. Here's a better way I really like, and that's to make the photons inside the cavity in the first place. So there's something called a Raman source, where you have a classical control field and a two-photon transition, which can take the atom from the ground state through an auxiliary level to an excited state, emitting one photon into the cavity while it does it. And likewise for the other side. And now all you need to do is put the two atoms in a superposition of ground and excited, hit it with one control pulse, and it'll put a single photon into a superposition of in that cavity and in that cavity. So we let it run for a while, vibrating mirrors and all the rest of it. If there's gravitational decoherence going on, then when we try to undo this and rewrite the photon back into the ground state, it won't work perfectly, and we'll get some loss of visibility in this kind of interferometer. So we put an entangled photon into the two cavities, let it interact with the mirror through radiation pressure for a while, and then try to rewrite it back into the entanglement inside the atom. And if we can't do that to arbitrary precision, then that's evidence of some other quantum channel. And if you're careful, you could make it dependent upon gravity. So that's essentially the idea in Stephanie Vanna's Nature Communications paper from 2016. And if you are interested, you'll see the details of what's required for the experiment there. It's also well understood in quantum optics how to put two of these Raman atoms into a superposition of ground and excited states, and therefore to produce the photons in a superposition between the two cavities. It's called the Koch-Lovett scheme. It was invented not that right? I think, no, it was Sean Barrett and Brendan Lovett. I came up with it, I think. I think Peter Koch was involved as well. I can't remember. Perhaps, do you remember, Farid? Anyway, some combination of Barrett, Lovett, and Peter Koch. And it's the basis of the sorts of experiments that are being done in Delft by Hansen to give loophole-free tests of Bell's inequalities. And there are dozens of other tests. Here's just a quick sampling. Ideas from Rob Bann in Waterloo in Canada, ideas from people in Belfast, I think, is that where Mara is? Yep. Other people, Marcus Aspermeyer, who I've worked with a lot over the years on this problem, and Martin Planio recently had a really clever idea of using a large mediating mass to couple two smaller masses. So the optomechanical tests are well underway to try and test gravitational decoherence in this mechanical setting. But what I want to talk about for the rest of this talk is something which hasn't been done yet, but I would like to see done, and that's photonic tests of gravitational decoherence. After all, our very best tests of general relativity are all optical, if you think about it. Well, at least some of them are. Things like the Shapiro shift, gravitational redshifts, and so on. Most of these are optical. The gravitational redshift is measured in optical clocks in NIST to, can measure gravitational redshift over the order of meters or less than a meter using optical clocks and gravitational redshift. So they're some of the very best experiments in all of physics. So why shouldn't we be looking at those as a test of gravitational decoherence? And finally, are there any purely photonic tests of gravitational decoherence? So here's the idea. Let's go back to Penrose again, who said that a superposition of a single mass in two different positions with respect to the Earth would lead to a non-stationary space-time. It would lead to a space-time which is not an energy eigenstate. Even if you could quantize it, it wouldn't be an energy eigenstate. It has to be non-stationary. So let's take that as the primary idea and not start looking for other forms of decoherence. Let's just take that as a given. Here's the basic idea. We have a mass in a superposition of two positions, and that will cause fluctuations in a redshift on this clock. So can we find really good clocks where fluctuations in the redshift would be self-evident? Well, the very best clock of all is a single photon pulse. Why is that? Well, then we take a detour through this beautiful work by Magdalena Zitsch at the University of Queensland, although she did this when she was a PhD student in Vienna with Jocelyn Bruckner. And it's in her thesis, Quantum Systems Under Gravitational Time Dilation, which is published by Springer. And you write down a perturbative expression for the Hamiltonian, and you find that in terms of the Newtonian potential, you pick up this term. So the rest mass now is a combination of mc squared plus whatever internal degrees of freedom this particle has. So an atom in a ground state will have a different mass from an atom in the excited state because it has slightly higher energy. So this thing here is the general relativistic time dilation of the internal dynamics. And that means, effectively, the gravitational potential will turn up as a change in the local flow of time, if you like, for the internal degrees of freedom. Now, here's the next step in the argument. We know that the classical gravitational fields we have around us are incredibly highly excited. Even if you buy gravitons, one thing for sure is the fields we have around us are unbelievably highly excited coherent states of whatever the gravitational degrees of freedom are. So we're not going to try and look for single graviton effects. We're going to try and look for the fluctuations around these mean field type states is one way to think about it, and see what effect it would have on the redshift. So we include quantum number fluctuations in the coherent state, and that will lead to decoherence of the internal degrees of freedom. So small fluctuations around a coherent state, at least the coherent states we understand in quantum optics, should lead to fluctuations in the internal degrees of freedom. So let me give an example from quantum optics. The idea here is we can have a dipole transition inside a cavity. It could be a superconducting junction dipole, which is the way I tend to think about it. And we inject in a laser field, and then it comes out. So the nice thing about this, if we keep it well off resonance, it just leads to a phase shift of the field. It is an effective two-photon transition, which leaves the atom in whatever state it started in, absorbs a photon and emits a photon. So from the point of view of the field, this is an atom-dependent detuning. From the point of view of the atom, it's a dynamic Stark shift due to the intensity of the light in the cavity. So you can just imagine what the trick is going to be. Put the atom into a superposition of ground and excited state. Notice in this Hamiltonian, the free Hamiltonian for the atom and the field is the constant of the motion. So this kind of interaction will always conserve energy. And that sounds like a good place to start. So here's how it would work. You would put the atom into a superposition of ground and excited states and the field in the cavity in a vacuum. Then you inject a laser into the cavity, watch it evolve for some time. You have to make the cavity leaky because the light can come out. And so you include all that, and you find that the density operator for the whole kit and caboodle, the atom plus field, that goes into, I should have made that G and that E, but it goes into this mixed state where there's some decoherence going on in the off-diagonal terms dependent upon CT. What the CT looks like? Well, these coherent states, one gets displaced one way because one detunes the field in one direction, and then the cavity driving will push it to some other amplitude, and likewise for the other detuning. So the field goes into coherent states, but the whole thing goes into a superposition of coherent states, which is highly non-classical. And gamma here is the cavity line width. The key parameter is this C. It has a short time quadratic exponential quadratic dependence, which is incredibly short. And then it has this even faster decay. Well, it's an exponential decay, but it goes essentially as the square of the separation as to where these two coherent states get displaced. So the slightest displacement of these two coherent states will almost instantly lead to the destruction of the off-diagonal coherence in this picture. So the very attempt to form a superposition of coherent states in this picture will lead to decoherence of the semi-classical degree of freedom, the radiation field. And you can show, and this has been measured, it's a relatively straightforward experiment in superconducting quantum optics. You can measure it and so on. I think it was first demonstrated by Serge Haroche using beautiful experiments for which he won the Nobel Prize. In the steady state, it just goes to a mixture. It's not surprising. All you're really doing, if you think about it, is trying to measure which state the atom is in. One coherent state will get pushed one way if it's in the ground state. The other coherent state will get pushed somewhere else if it's in the excited state, because they have different detunings. In phase space, they look something like this. One steady state gets pushed up there, sort of spirals out, and this one spirals out to here. So these are sometimes called the pointer basis states, because they're essentially like a pointer telling you whether the atom was in the ground state or the excited state. And they are pointer basis states because of the particular way the cavity is coupled to the external world. And what you get as pointer basis states depends on what you have in the irreversible coupling, which is Zurich's idea from many, many years ago. So if you now measure the phase shift of the field, you can obviously tell whether you're in the ground state or the excited state. It's just a measurement after all. We just check if the field went that way in the phase or the other way in the phase. And these sorts of experiments are very, very common in quantum optics. So now let's go back to gravity, and I better quickly finish. Taking Magdalena Zic's Hamiltonian, but imagining now we quantize the gravitational field through some linearized model, H0. We'll pick up a term I'm not an expert on quantum gravity, so I can't explain exactly how this works, but if you want to, it's in Klaus Kiefer's book. Then you get the coupling between the internal degrees of freedom in the de Donda gauge. Doesn't involve any exchange of energy between the field and the atom, just like in the coherent state quantum optics experiment I just described. But what it will lead to is fluctuations in the size of this term here, which will appear as redshifts, fluctuating redshifts. And these are creation and annihilation bosonic operators for gravitons in the field. You could quickly derive from that very easily what you would expect for the gravitational decoherence equation for the internal degree of freedom. And it picks up this commutator, double commutator with H with the internal. Now, because the energy commutes with H internal, this means that this will not violate conservation of energy. Energy will still be conserved. And there's a way to make a complete Lorentz invariant so it doesn't break Lorentz invariant. What it will do is cause decoherence in non-stationary states. So the minute you try to do some dynamics, which involves superposing stationary states, you'll begin to see evidence of this term. And this goes back to work done by Gambini and Poulin many years ago in some of their ideas, thinking about ways to do loop quantum gravity and discretized general relativity. And it's some work I did years ago as well in trying to understand limits to clocks if there are fluctuating fields around. So what's that got to do with photons? Well, let's think about the Shapiro test, which is a delay of an optical pulse or a radiation pulse of some sort passing close by a massive gravitational object in the sun. And so there's some little delay, which is given by this formula here. This is essentially the gradient of the potential, log 1 minus r dot x, where these are unit vectors defined in this way. One pointing to the mass source and one pointing to the source of the radiation. So those tests have been done, and they work, and general relativity predicts the results extremely well. So what we're going to do is something similar, but at a single photon level. So the idea is this: we use a single photon source and a single photon detector, which are made regularly. They form a key component of a great deal of modern quantum technology involving linear optical quantum computing and spectroscopy and ion trapping and so on. And they're based on Raman devices once again. So depending on the shape of this classical control field, you can shape exquisitely this single photon pulse that comes out. And just by reversing the whole thing, you can make a quantum memory which will read that photon pulse completely back into a detector, so long as there's no dephasing going on anywhere. So that's what we're going to do. What is a single photon pulse? Well, people get confused about this. They think it's just a weak coherent state, but it isn't. A single photon pulse is indeed weak. It's only one photon after all. But a coherent state has on average one photon, which most of the time means it has nothing, and sometimes has 2 and 3 and 4 according to some Poisson distribution. But a single photon state has 1. The average field of a single photon is 0 because it has random phase, but the intensity is extremely well defined. If you work out the rate of detection, you find that it's given by A dagger A for a single point detector. That's the standard Glauber theory of photodetection. And so you get this space-time probability distribution for detecting that single photon, which is given by the Fourier transform of this superposition amplitude here. If you think about what this is, it's a superposition of one photon of all frequency modes. So it's like 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, highly non-classical. And that is in fact a superposition over energy eigenstates, because the energy eigenstates are eigenstates of a particular frequency mode, as an energy h bar omega. So single photon states are necessarily a superposition of energy eigenstates in this fashion. They lead to pulses, and the Raman detector can be configured to detect these pulses with probability 1. And in fact, you find if mu t is the control pulse of the detector, and you make this state with the source, the probability of detecting it is just the overlap between those two states, bounded between 0 and 1. Now, in optical terms, a single photon pulse that's a pure state is called transform limited. So these states are single excitations of the electromagnetic field, little pulses that are transform limited, which have average field 0 and well-defined intensity as a function of time. So here's the idea that just shows if the whole thing is completely reversible, then you should be able to create it and detect it without any uncertainty. Pure states are transform limited. Gravitational decoherence will add phase noise, and therefore they will no longer be transform limited, and therefore this protocol will fail with some probability. You can actually work out what it is using pretty standard, well, not standard, but using Gambini and Pullen's arguments, other people's arguments, what gamma should be. You can show that the probability of detection in this case has this Gaussian suppression term. If gamma is 0, these integrals factor, and each one is 1 by normalization. But if there's gravitational decoherence, you pick up this term. So you can stick in some typical examples. You can put in a Gaussian example. So this is a Gaussian pulse where the spread in frequency is 1 over alpha. So if alpha's small, it means the spread in frequency is really big. So it means a really short pulse. And you can compute what that probability is. And it's given by this. Here I've written in terms of a fundamental time, which is h bar squared times gamma, if you go through the units carefully. And so what you have to do now is trying to arrange a situation where t, tau, and alpha is something not too infinitesimal. Now we expect tau to be pretty small, otherwise we would have seen this. You could really take a pessimistic view and put in the Planck time and work out exactly what sort of experiment you need to do. It's not easy. Turns out you need to propagate the photon over, millions of kilometers. But you can make alpha pretty small by making the pulses incredibly short. So that's another way to boost the experiment. So I haven't got a proposal to put to you right now. I'm working on various ones involving mapping optical photons around massive cylinders and so on, or some astronomical observation. But there's a good chance that experiment could be done. So as I said, it's going to require very short pulses and incredibly good optics and very good detectors to do this experiment. But at least it's a change from looking for heating due to Penrose Diosi type gravitational decoherence. So with that, I'll finish and just thank my collaborators. Thank you very much.
So you talked about different schemes,
Mhm.
measurements that could be done. I mean, what about the experiments? How actually?
Okay, the experiment in Italy was done and involved looking for heating in some massive array of nuclei in some low temperature experiment. Didn't find it. The other experiments are all underway. So the atom optical experiments are being built in lots of places around the world, getting the vacuums low enough, the temperature low enough, the particle trapping low enough to actually put a decent bound on what the gravitational decoherence is. Of course, I should say that in the absence of a quantum theory of gravity, all we can do is do experiments that put a bound on what quantum gravity effects are. We can do an experiment the best we possibly can, and we see no decoherence, then we know that the coupling to gravitational field is somehow smaller than that. So yeah, the experiments are all underway. There are lots and lots of results coming out showing they're getting closer and closer and closer. So people in UCL, Vienna, lots of different places pushing ahead with these experiments in the optomechanical case.
How can we prove that the decoherence is due to other interaction?
Yeah. I mean, looking for decoherence is a bit like a hopeless task, really, because you have to rule out every other kind of decoherence before you can say it's due to gravity. So that's why the experiments are taking a long time. You first have to know all the other sources of noise in the experiment and control them to an extraordinary degree. But you're also looking for some smoking gun that it's gravitational decoherence, which will always have some, depending on your favorite model, like Penrose and Diosi models, it will have a particular dependence on the mass distributions that you're using. And so you'd be looking for that kind of heating. You'll also be looking for heating that had nothing to do with actual temperature. It's due to some unknown degrees of freedom which can't be eliminated from the experiment. So clearly these experiments have to either be done at very low temperature or very high frequency, which is why I favor the optical tests, because at optical frequencies, the world is indeed very cold.
Another one?
Mm-hmm.
Might sound a bit controversial, but
Good.
there are proposals that suggest that, for example, gravity is not really a fundamental force. So
Good question.
There are like these
Entropic gravity of for Eric Verlinde.
not think about whether this is
Any
kind of
yeah.
more problematic than the proposal.
Yes.
But there are ideas that is Saskin did a paper that was titled was QM equal to GR. Was basically arguing that you cannot have every time you have quantum mechanics, you must also have gravity. There are papers that tend to make the thing more precise. But I was wondering, are these
Not all are immune to that criticism. So entanglement witness ones should be, if they're conducted properly, but others that just look for unknown fluctuations will be open to those kind of criticisms. There was a very recent paper from Martin Plenier discussing exactly that issue. I don't remember the title, but it was on the archive in the last 12 months or so. But yeah, that's a very good question, actually. There could be other theories of gravity that don't require necessarily some gravitational degree of freedom, but lead to heating or fluctuations or something. But they will never be able to be used for entangling particles if they're classical. Yeah.
Why should we expect to see effects of quantum gravity at the scales that we do experience? Because intuitively, as a field theorist, quantum fluctuations in gravity are Planck suppressed.
Yep.
All quantum effects. So
Yes.
why should we even expect to see?
Well, it's like in quantum optics, we saw evidence of the quantized radiation field long before we detected single photons. It was spontaneous emission. Now, there were attempts to explain spontaneous emission semi-classically, and they all get the wrong rate by a factor of 2. So we know in the history of quantum optics, long before we saw photons, the granularity of the field, there were clear predictions of what a quantum field theory of light would suggest. So it's the same thing here. We're looking for those sorts of effects. So effects coming from intrinsic quantum fluctuations, not from probing single particle excitations of the gravitational field.
Except that the gravitational coupling and coupling of the photon field to charges, what is the magnitude?
Yeah, absolutely.
Alpha versus alpha gravity is
Yep.
So, as a field theorist, I would think that any effect that tries, any experiment that tries to probe quantum mechanical aspects of gravity doesn't have a hope in hell.
That's what people have been telling me for the last 20 years.
What is the,
That's why we did, that's why these calculations have been done, to show.
So what is what causes the enhancement? What is it that
Incredible advances in quantum technology to produce superpositions of massive particles. The Planck mass is not very small. It's, I don't know, what is it, micrograms or something? It's not very small. It's exactly where you will be able to produce decent sized superpositions of massive particles. So I agree, it's completely different from the electromagnetic field, but the calculations show that at some point in these massive interferometry experiments, you will begin to push on reasonable expectations for gravitational effects due to entanglement. So they're basically interferometry experiments of one sort or another. And we're not trying to probe fluctuations in, say, the electromagnetic field due to quantum excitations of the gravitational field. It's not that kind of experiment, which would indeed involve huge, huge energies. But, you know, I understand your skepticism, because at first sight, that looks to be the obvious objection. And that's why we've been pushing and pushing hard on these sorts of calculations. Now, as I say, in the absence of quantum theory of gravity, all the experiments can do is put a bound on what these decoherence effects should be. You do the best experiment you can and you don't see it. Therefore, it's smaller than that. But that is already pretty good. There's already experimental evidence. There was some work I did some years ago with Jake Taylor in Maryland, asking, suppose gravity is a classical channel. That is, effectively, it measures the position of a particle and takes a classical measurement result in a finite amount of time over there and tells that one how to move. So you can write those theories down and work out exactly what happens, but they're ruled out by astrophysical observations. So those theories are already ruled out by astrophysical observations. So whatever gravity is not a classical channel.
So are there any other questions? So if we don't have any further questions, then thank you for coming. Thank you, Gerard, for being with us. And then we can continue having snacks and tea and informal discussions as we wish. And let's thank Gerard again.